Great, I can see people coming in. So the next session will be chaired by Bartek. I think everyone know Bartek, so who organized our last year's MIUA. So I'll hand it over to you and introduce the first speaker.
Thank you very much. So I will be chairing this session, and our first talk is from Francesco, who will be talking about the correlation between the morphological features and manually annotated features for lungs extracted from CT images. The floor is yours.
Okay, thank you very much indeed for the presentation. In this work, I'm going to present correlation analysis between manually assigned radiological attributes on lung nodules at CT and computer calculated features. Briefly, this is the outline of my talk. I start with the introduction, then I'll describe materials and methods, study population, shape features, and statistical analysis. I present the results, discussion on them, and I conclude with some final considerations and direction for future work. Okay, let's give some background to this work. Incidentally detected lung lesions on computer tomography are quite common findings in the clinical practice. It is estimated that around, well, a small fraction of these abnormalities actually represent malignancies, around 5%. And of course, it is the correct assessment of suspicious lesions is important to maximize the treatment outcome. And radiological assessment, of course, involves the analysis of a number of morphological features that the radiologist needs to score. Well, in this context, we all know that in recent years, radiomics has shown potential to improve the discrimination capability between benign and malignant suspicious lung lesions. Well, the basis of radiomics are that it can detect features that would otherwise go unnoticed to the human eye. And radiomics, of course, translates images into quantitative parameters, and these parameters can be processed through artificial intelligence and machine learning methods. Of course, there are limitations to this process. There are technical ones as well as user experience ones. As for the technical ones, there's a problem of standardization and data availability. Regarding the man-machine interaction, so to speak, we have problems of interpretability, provenance, and accountability. And in particular, in this work, we were concerned with standardization and interpretability. So let's clarify the objectives of this work. So what we investigated the correlations, as I said, between computer calculated features and manually assigned radiological attributes. We did not investigate in this work the accuracy of prediction models. This has been done many times in the past. We didn't do that again here. Okay, let's have a look at the materials and methods, starting with the patient series. We consider a data set of 300 lung nodules, suspicious lung lesions, from 158 patients. So some of the patients had multiple nodules. The source was the open access lead-IDRI dataset. Each nodule comes with manually annotated scores about a certain number of attributes. I'll talk about this later. And the delineation of the region of interest. Would like also to stress that this is a multicentric, therefore heterogeneous dataset. Actually, the whole of the lead-IDRI dataset contains around 1,000 images, 1,000 nodules. But in this work, we consider a subset of the whole data set. And our inclusion criteria were that at the scan level, there should be a complete data record as regards the age and gender of the subject and image acquisition settings. And at the nodule level, we require that there were at least 3 different annotations from as many radiologists for each nodule. Okay, so what were the manually assigned radiological attributes that we considered in this analysis? We considered 3 attributes. Lobulation, in the first row, with increasing value from left to right. Lobulation is related to the shape of the border of the lesion and the change from convex to concave border, sorry. The second one was sphericity or roundness, again with increasing values from left to right. And the last one that we consider in this work was speculation, which is also known as the corona radiata sign, again with increasing values from left to right. For each of these attributes, there are manual scores assigned by the radiologist, and we consider for each nodule the average score for the correlation analysis. On the other side, we consider 9 computer-calculated morphological features, and the features that we consider are all dimensionless and compliant with the IPSI standardization initiative. So we have area density, sphericity, compactness 1 and 2, elongation, flatness, spherical disproportion, sphericity, and volume density. Okay, these features depend on, they have quite simple definitions. They depend on the area and volume of the region of interest, area and volume of the bounding box, and length of the principal axis of the region of interest considered as a mass distribution of uniform density. Importantly, I want to underline that some of these features are actually not independent to one another. They can be derived from one another through simple mathematical transformation. This is another point to which I'll come back later. The computer calculated features were extracted from the 50% using the 50% rule. That means that one voxel was considered within the region of interest if at least a half of the annotators marked is in the region of interest and outside the region of interest otherwise. For the correlation, we investigated for the correlation analysis both linear and monotonical correlations between the 2 groups of features. Therefore, we use Pearson's and Pearson's linear correlation coefficient and Spearman's rank correlation coefficient. The implementation, we use Python and a number of Python libraries. The experiments were carried out on a laptop computer, and the total execution time was around 1 hour. And importantly, there is a GitHub repository where all code and data needed to reproduce the experiments are available for free. Now let's have a look at the results. Hold on to your seats. This is the table showing the results of the linear correlation analysis. Rows indicate the computer calculated features and columns the manually assigned radiological attributes. There are 3 things to notice. The first one is that the strength of the correlation was at best moderate. So we got the highest value in absolute term of around 0.6, which is rather good, but not very strong correlation. Regarding the sign of the correlation, That was more or less as we expected. That means that, for instance, we have that asphericity correlates positively with lobulation and speculation. That compactness 1 and 2 correlate negatively with lobulation and speculation. So more or less the sign of the correlations that we obtain were what we would reasonably expect. The third point, and this again was not unexpected. Of course, the features that can be derived from one another, for instance, compactness 1 and 2 and sphericity, gave the same results. Same happened with asphericity and spherical disproportion. The Spearman's rank correlation coefficient didn't return significantly different results from the linear correlation analysis, so there's not much to add to this slide. The trend was more or less the same as we obtained for the linear correlation analysis. Some scatter plots to visualize the data. This one, for instance, about between lobulation, manually assigned lobulation, and asphericity. So we can see that there is a certain trend, but of course, there is also a significant dispersion of the data. This one is quite interesting. It's between sphericity and flatness. There is a positive correlation, which could seem quite counterintuitive, but actually it's not, because the IPSI definition of flatness is reversed in the sense that low values of flatness indicate flat objects, and high values of flatness indicate equant cuboid objects. So this trend is perfectly consistent with the definition of flatness given by the IPSI. Last one, about speculation and asphericity, again, positive trend, but significant dispersion of the data. Okay, so just to summarize the main points of this analysis. So we were quite surprised that the overall correlation strength was at best moderate, because in previous studies a stronger correlation was reported. However, in that study, the analysis was performed on synthetic tumor models, which can explain the difference. As I said, the sign of the correlation was consistent with the definition of the features and the morphological assigned and the manually assigned attributes. And we have redundant features, and we need to get rid of them, as I see it, because they can only generate confusion in the end. So in conclusion, standardization and interpretability are two main issues in radiomics. And in this context, in this work, we have investigated the correlation between computer-calculated morphological features and manually assigned radiological attributes. Strength of the correlation, as I said, was lower than expected. The sign of the correlation was consistent with the definition, and we have a number of redundant features. Limitations, there are some limitations, of course, to this analysis. First of all, it was a retrospective one. We used a multicentric, therefore heterogeneous data set. And we performed the analysis, the statistical analysis on aggregated measures as regards the manually assigned attributes, which means that we did not investigate inter-observer variability, for instance. That would be interesting subject for a future study. Some other directions for future work. I think it is important when in most cases we are obsessed with accuracy of prediction models. That's fine. I understand that. But I think that interpretability is also very important. So it would be important and interesting to define new features with focus on interpretability. It might seem not an important result, but the fact that we have redundant features is something bad. So if we aim to standardization, there shouldn't be redundant features. If there's a cluster of redundant features, you should just keep one representative of them and get rid of the others, or declare them superseded. And lastly, when we talk about morphological features, we shouldn't forget that there are already existing standards, whether used in other contexts, for instance, in particle size analysis, but where many of the features that I have talked about in this work are already defined. Okay, that's it. And thank you very much for your attention.
Session is now open for questions. So any questions from audience? Carlos? No.
Thanks a lot for the talk. So you compare the radiomic features to hand annotated features by experts, but in some way we know that experts tend to be inconsistent and they tend to not necessarily always annotate with high accuracy everything. So do you think, even if so, obviously there is just moderate correlation between the automatic ones and the hand annotated ones. Do you think, or what's your opinion on the actual relationship to the illness or to the to the actual clinically relevant thing in the end? Do you think it will be higher with the automatic ones, or is it just really that the automatic ones are not they don't have enough explainability or enough power to represent?
Okay, this is a very interesting question. I think there are 2 points. First, about the fact that different annotators can give different scores. As I said, we didn't investigate that. We just took the average, and so we didn't go for that kind of analysis. And also, we did not investigate, we were not concerned with accuracy in general, but just with interpretability in this work. But of course, this could be an interesting direction for future research. But I must add one more thing. This data set, as I see it, is not particularly good for performing accuracy analysis on prediction models regarding malignancy. Why? Because only a small part of this data set has a pathology ground truth. Most of the nodules have a manually annotated ground truth. So it would be complicated to carry out that kind of analysis. We need a reference standard, a histology standard to do that kind of analysis. But yeah, interesting.
Another question?
My question is related to that one. So for when you get the manual annotations, then you average the 3, or how do you get it? Because if you have equation and then they go like that, then the average can be removing a bit the feature that you're trying to get.
Okay. There are 2 things. The annotations are about the manual score for each of the attributes, for instance, speculation, sphericity, and lobulation. That is one thing. And then you have the delineation. So each radiologist gave one delineation, and we put them together using the 50% rule. We kind of consider an average ROI. with the rule that one voxel was considered within the ROI if at least a half of the annotators consider that in the ROI and outside the ROI otherwise.
Any other question from audience? There is one more.
Thank you for a really nice talk. I really enjoyed that. I definitely take your point about extracting parameters that clinicians can understand. From a statistical point of view, is it possible to take in confounding factors as well? Instead of just building up a simple kind of univariate or bivariate correlations, can one build up more sophisticated models that adjust for these other factors?
Okay. Yeah, a couple of things. About the confounding factors, yes, in principle, there are confounding factors, for instance, due to the fact that this is a heterogeneous data set. And so, for instance, the resolution of the images vary. But previous studies have demonstrated that the morphological features are actually quite resilient to that kind of variation. Regarding the statistical analysis, we went for linear and monotonic correlation because that we thought would make sense. I mean, the higher is the value of a manual assigned attribute, the higher should be the value of a computer extracted one. But we could also think of more sophisticated statistical analysis of independence, for instance, through, I don't know, Hefting distance or something like that, but we didn't do that in this work.
Would it be possible to model the shape directly and use something like principal components regression or partial least squares methods?
This is okay. Yeah, it is. But in this work, again, we made a choice to use only standardized features. And we mean standardized, we mean that defined in the IBSI by the Image Biomarker Standardization Initiative.
Yeah, I thought it was a great talk. Thank you very much.
Thank you very much. And we need to move to the next talk. So the next talk is going to be given by the next talks will be given by the online participant. I think it's Zeyuzu, who will be talking about the large-scale patch-wise pathological image feature dataset with hardware-agnostic feature extraction tool. So yes, please start.
Hi, can you guys hear me? Can you hear me?
Yes.
Okay. Hi, my name is Zeyuzu, and I'm a member of Biomedical Data Representation and Learning Lab. And today I'm going to present our paper. And so the contribution of this study is fivefold. So firstly, we released a foreground patch level feature dataset and saving 92.1% of the storage space and 140 days of the computational time. And secondly, the global spatial location of the patch level feature is provided to aggregate whole site image level results. And thirdly, the feature dataset from two pre-trained models, ImageNet and the Big Transfer, which we call BIT, and the two resolutions, 1024 and 2048, are evaluated and released for flexible downstream analysis. Fourthly, we containerize the foreground segmentation, tiling, and feature extraction steps as an operating system and a hardware agnostic Docker toolkit called the PAS container to allow for convenient feature extraction. At last, the entire PAS feature dataset and the PAS container software has been made publicly available. Okay. Yeah, this is like a brief description of the PAS feature dataset, and it consists of host images from both the Cancer Genomic Atlas Program Repository, we call it TCGA, and the Pathology AI platform, we call it PIP. So the raw host images talk about 15 terabytes, and after the feature extraction process, it saves like 92.1% of the storage space. So it saves a lot of space. And for the method part, as we know that pre-processing of the large-scale gigapixel whole cell images is very resource intensive. And also most of the whole cell images regions are typically background, as you can see from the image to the left-hand side. And so to obtain the comprehensive foreground patch level features, we implement foreground segmentation, tiling, and feature extraction using the proposed path container processing toolkit. So this slide briefly describes the foreground and the segmentation process. Briefly, the existing foreground segmentation and tiling algorithm are employed to achieve image patches of 2016 times 2016 or 512 times 512. So for the feature extraction stage, path container incorporate different options that allow users to choose from, like the patch resolution 256 times 256 or 512 times 512, or like a pre-trained model if you want to use ImageNet or like big transfer, or the feature dimension 1024 or 2048. The ImageNet pre-trained ResNet 50 model is employed, which utilize adaptive mean spatial pooling after the third block of the ResNet 50 in order to get feature vectors with a dimension of 1024. And we can obtain 2048 after the fourth block of ResNet 50. So beyond controlling the output dimensionalities, we also employ the BIT model as another pre-trained model. Similar to ImageNet 1024 and ImageNet 2048, we also include 1024 and 2048 dimension vectors for big transfer, and it is also provided by path feature. Okay, to evaluate the efficiency and the effectivity of the path feature dataset and the path container Docker, we perform a downstream weekly supervised tumor segmentation task using the claim segmentation pipeline. So in order to, in the original claim design, ImageNet 1024 was employed as the pre-trained patch level feature model. So in our study, we extended the design with ImageNet 1024, ImageNet 2048, BIT 1024, and BIT 2048. So by using the whole cell image level weak classification model, claim classifies each image patch with a cancer score. As you can see from this picture, the heat map and the tumor segmentation masks are utilized to evaluate different feature extraction strategies via path container. So to allow for convenient pre-processing with single line of command, path container is developed as a Docker image. Path container consists of the following three steps: foreground segmentation, patch tiling, and feature extraction as mentioned above. All the required libraries are included in the Docker file, which is publicly available. So in our GitHub repository, path container includes three major parameters: an input directory to save the input whole cell image file, an output directory to save the output features, and a configuration file to specify both the Docker file and the configuration file. Okay, so this figure compares three different whole cell image processing pipelines. So the upper panel represents the tissue segmentation and the processing command line tool called PyHist. The middle panel represents a weekly supervised method that uses an attentional-based learning process called claim. And the bottom one is our containerized path container toolbox, which allows users to customize the pre-processing steps with different patch size and the feature extraction algorithms, and the feature dimensions. So the past feature dataset consists of host image from both the TCGA dataset and the PIP dataset. So TCGA dataset includes various types of host images like kidney, liver, prostate, pancreas, and etc. The PIP dataset consists of 6 types: liver, colon, prostate, kidney, pancreas, and bile. We use PAS container to extract features from all of the 14,000 POSI images with ImageNet 1024, ImageNet 2048, BIT 1024, and BIT 2048. So ultimately, it will provide a total of 56,000 .h5 files. 940 host images of renal biopsies were employed from TCGA dataset, which contained 3 subtypes of tumors for the kidney. So 519 kidney renal clear cell carcinoma, it's a TCGA KIRC, and 300 kidney renal papillary cell carcinoma, that's a TCGA KIRP, and 121 kidney chromophobia, that's a TCGA -KICH. Throughout the feature extraction process, PAS container obtained 4 types of patchwise features. As I mentioned before, is ImageNet 1024, ImageNet 2048, BIT 1024, and BIT 2048. So the process generated 3,760 .h5 files containing both features and the global coordinates for each patch. The model will train and apply to an external testing dataset with 44 renal cancer host images from PIP dataset. So for the PIP dataset, the tumor area will manually traced by pathologists. So this figure shows the storage space consumption for 14,000 feature extracted from 2 datasets. So the extraction method includes above 4 methods that we mentioned, and the feature of dimension 1024 are only about 7.8 of the rows dataset. Features of dimension 2048 are only about 15.5 of the row dataset. Directly learning from the row dataset, the pre-processing for feature extraction from 940 host images took about 456 hours. By contrast, the downstream supervised training only requires around 20 hours for the task of training each model. The figure represents the qualitative tumor segmentation result on 2 randomly picked testing host images. 940 host images from TCGA were used as training and validation dataset, while 44 host images from PIP were used as independent external validation. The heat maps and the masks were computed using CLAIM, and the different heat map based visualization. So the red part represent the high probability of a tumor, and the blue part represent a low probability of tumor. And the weakly supervised tumor segmentation masks were from different feature types is included in PAS feature. And in this figure, it represents the qualitative testing result of weakly supervised segmentation using different per-chain model in PAS container. And as we can see, the corresponding quantitative results. So it's a dice score of weakly supervised tumor segmentation result were trained by, were presented, and it is trained by 940 host images. The ImageNet 2048 and the BIT 1024 feature dataset achieves a superior segmentation performance. So here's the conclusion. In this paper, we released and evaluated the PAS feature dataset, a large-scale patch-level image feature dataset from the TCGA and PIP cohorts and compare with processing from raw host image files, PASS feature saves 92.1 of the hardware storage space and 33,360 hours of computational time. Meanwhile, we released PASS Container, a containerized pre-processing toolbox for host images that includes foreground segmentation, patchwise tiling, and feature extraction. The prevalent ImageNet pre-trained model, as well as the recently developed big transfer model, are provided through PASS Container. So using a subset of 940 host images, the efficiency and efficacy of the PASS feature and the PASS Container were evaluated and by different feature types. So the result indicates that ImageNet 2048 and the BIT 1024 achieves the superior segmentation performance. And yeah, thank you so much for your attention.
Thank you very much for your presentation. So session is now open for questions. First volunteer for questions. Or maybe I will start then. Can you comment or can you give us some insights how the feature you extracted from those two different cohorts, how they could generalize into potentially some other data sets? So how far we could transfer them into some other task from other cohorts beyond those two cohorts you have already included?
Yeah, sure. So so it includes the feature extraction process, which we utilize mainly from the claim repository, and basically we extend the claim repository to for the claim repository, it only includes like using ImageNet for features with dimensionality of 1024, sorry, and we extended to use big transfer and with different dimensionalities. So if people can just use our toolkit, the PASS Container Docker, they can just import the host side images from other data set, and it will automatically compute it for the features for them with the dimensionality and the model they choose.
Thank you. Carlos, do we have a microphone?
Thank you. Can you go back to your results in slide 13?
13.
That one.
This one?
No, 13, that's 12. That one. So
Okay.
The subject number 2, your prediction is very close to the binary mask, but in subject number 1, your prediction is predicting more outside the mask than inside the mask, in particular for ImageNet 2048. Can you comment on that?
Yeah, so I think there is for the first one, the tumor part is mainly the middle circle section, and that's and also for the subject 2, the all 4 model did a pretty good detection on the heat map. So I think it's just I mean, it just probably they didn't do a pretty good job on the subject 1. Yeah.
Thanks. Let's thank speaker again. And the last talk of this session is presented by Maldonado Garcia. And Maldonado will be speaking about predicting myocardial infarction using the retinal OCT imaging.
Hi, everyone. My name is Cynthia Maldonado. I am a PhD student from the University of Leeds, and today I'm going to talk about predicting myocardial infarction using retinal optical coherent tomography imaging. Well, first I'm going to talk about the background. Cardiovascular diseases remain a major cause of death globally. In 2019, it was reported that around 17.9 million of deaths worldwide, representing 32 of all of deaths were because of cardiovascular diseases, which more than the 3/4 were in low and middle income countries. Of these deaths, 85% were because of myocardial infarction and stroke events. Therefore, it is essential to use cost-effective imaging solutions to identify patients at risk of cardiovascular diseases to enable widespread screening of large population in low and middle income countries. Recently, retinal images have been used to assess retinal vasculature and derive ocular biomarkers for predicting cardiovascular diseases. These retinal imaging have several advantages. The first one is they are non-invasive techniques. The second one is retinal images such as fundus photographs, which is the imaging in the top, and the optical coherent tomography, which is the imaging in the bottom. Well, these retinal images routinely are obtaining in opticians, in clinics, and in hospital for screening for several eye conditions. But will fundus photographs provides information about retinal vascular health. They are 2D images and don't provide detailed information of retinal microstructure and retinal microvasculature. And also, these retinal images are relatively inexpensive compared with cardiac magnetic resonance, which is the typical medical imaging to characterize cardiac function and cardiac structure. Well, compared to fundus photographs, optical coherent tomography provides ultra high resolution 3D characterization of retinal microstructure and retinal microvasculature, and thereby assess, and also, well, it has been shown that the changes in retinal microvasculature are related to pathological changes in other organs. So combining deep learning and optical coherent tomography could provide the means for screening patients at risk of cardiovascular diseases. Therefore, the aim of our studies demonstrate that OCT imaging can predict future MI, myocardial infarction. To do this, we propose a task-aware variational autoencoder, which comprises 2 stages. The first one is the pre-training of self-supervised feature extractor, and the second one is the fine-tune of the task-aware variational autoencoder that I'm going to show you in a moment. But well, this first stage comprises, this first stage, well, it's, to train this first stage, we have the encoder and decoder, and we pre-training to enable the variational autoencoder to learn a rich representation in a self-supervised fashion. And well, this pre-training helped to learn the features that are using and are a good initialization for the next stage. The loss function for this first stage comprises 2 terms. The first one is the reconstruction loss, which is a mean square error, and the second one is the Kullback-Leverrier divergence, which is used to regularize the network by minimizing the divergence between the posterior distribution of the variables and the assuming Gaussian prior of the latent variables. And well, the second stage comprises two parts. The first one is the self-supervised feature extractor that is the architecture is the same like I showed you in the first stage. And here we have an additional fully connected classifier. Well, that I'm going to explain in a moment. The input to the framework are OCT, BSCAN, Imagine that are used to learn a compressed latent representation of the high dimensional data, which in turn is used by the fully connected network to distinguish between healthy subjects and those likely to suffer MI in the future. Well, the loss function for this second stage is similar to the one for the first stage when we have the reconstruction loss and the Kullback divergence. But here we have an additional term, which is a binary cross entropy loss, which is the classification loss. But here we increase the weight for this classification loss because at the end, in the second stage, we want to do a classification task. Well, for training a validate or model, we use OCT Imagine from the UK Biobank. Well, if we use 2,248 healthy subjects for the first stage for the pre-training variational autoencoder, and these were excluded for the next stage for the fine-tuned task-aware variational autoencoder. But here in the second stage, we have the same amount for myocardial infarction patients and the same amount for healthy subjects. So we can have a balanced data set. And we compare our model with a pre-training CNN, which specifically is the DenseNet 1-to-1. Well, to evaluate, we evaluate the performance of our model in two ways. The first one is its reconstruction performance, and the second one is classification performance. First, we evaluate its reconstruction performance, which evaluates the ability of the model to reconstruct the OCT images, and thereby assess the richness of the latent representation. So the reconstructed images, well, I'm not really sure if you can see, but the reconstructed images capture the global, which are like the biggest layers, and also capture the structure of the retinal layers, which are inside of the bigger layers. This explains also that our model is learning a richness representation of the latent space. And we also, we achieve an average of the structural similarity index at 0.98 from across all the test data set. Well, then we evaluate the classification performance of our task-aware variational autoencoder at the DenseNet. And well, our model outperforms the DenseNet in 4 classification metrics: in the accuracy, the precision, the recall, and the F1 score. It is visible that our model predict more MI patients than DenseNet, and we can see this especially in the recall because we have a higher mean percentage. However, this came with a cost because we predict less. We predict less true negatives cases compared to DenseNet, and we can see this in the specificity, which the DenseNet achieve a higher value. However, since we want to minimize the MI cases that being misclassified, we consider this to be a positive result for our approach. Then we calculate the ROC curve for both approaches. And the area under curve values for our task-aware variational autoencoder consistently outperformed the one obtaining for the DenseNet across all cross-validation faults. And the mean area under curve of the task-aware variational autoencoder was at 0.74, which is significantly higher compared to the DenseNet, which achieved a mean area under curve at 0.63. Well, according to these results and this study, we would like to address some questions in the future. The first one is, can multi-organ data help predict cardiovascular diseases? And the second one is, what are the features in the OCT images that are relevant for predicting cardiovascular diseases? Well, this brings me to the conclusions. The first one is the latent representation learned from OCT images using a task-aware variational autoencoder can be used to predict myocardial infarction. Our method outperformed conventional CNNet classifier, highlighting the advantage of self-supervised learning. And the third one is, based on the proof of the concept, OCT can be a cost-effective solution for identifying patients at risk of myocardial infarction or potentially other cardiovascular diseases. Well, many thanks.
Thank you very much for your talk. Session is open for questions. Yeah.
Hi there, thanks for the talk. I'm sorry I didn't have time to check the paper for details. Can you just go back to the slide? There's some images, which is from the original, and there's some images from the reconstruction. So I was very curious about why there's some like a unique style, like lying on the reconstructed images, more
Yes,
like not like blurred, but more like overlaid.
I forgot to mention. Yes, let me look. The OCT looks like the bottom one is the completely, but our data set divide this completely imagine in 128. So divide the imagine into 128 parts. So that's why in the reconstructor we are looking just a part of the completely imagine. Yeah, but this is our data set. It's a volume of all of the slices in the OCT.
And can you go back to the slides which shows the total framework? So I was wondering, have you ever considered an ablation study, which is remove the reconstruction and just test the latent and it goes to the classifier and to see whether the reconstruction can boost how much degree of the classification performance?
Well, yes. We made some experiments without reconstruction. The first one is we made first an experiment from the scratch. I mean, training only the encoder and the classifier without the decoder, but we have really bad results. It's in the supplementary information in the paper, because the accuracy and also the other classification metrics were really low. It's like 0.5. It's like it's not distinguished between the MI and the healthy patients. And then we made other experiments where we have we use the pre-training of the variational autoencoder, but then in the second stage we only have the decoder and the fully connected network. But the model was like overfitting, and I think it's because in a way the decoder is like a regularization of the method. So yeah.
Thank you so much.
There's
Thanks
another
to you.
question downstairs.
Thanks for speaking. I'm just curious medically. Is there like a large variety in how susceptible people's eyes are to getting damaged by their heart problems?
Yeah, well, I think it's a recently topic, but there have been many studies that are confirmed that the retinal images are used for cardiovascular diseases. There is some like say the how can I say the vascular in the retinal because it's the circulation. So maybe it's related to that. Yeah.
I guess some people's eyes will be much more resilient. There'll be like a big variety, or is not so much.
What do you mean? Sorry.
As in like if two people with the same heart disease might have very different reactions in their retina.
Let me see if I understand. You are saying like if people have different cardiovascular diseases can reflect in the eye or something like that? Or?
Yeah, it might just be different. Like there might be other factors that like determine how susceptible your eyes are to damage.
Yes, I think so. To be honest, I don't know. I'm going to.
I could actually follow up on that because you also, the last slide or one of the last slides, you said that you want to include like a multimodal data. And my question would be following kind of on your question is, instead of using the like MRI data from UK Bank, would be basically possible, for example, use like a patient metadata, age, gender, and so on, which possibly could also influence
Yeah.
how the microvasculature eye looks like.
Yeah. Well, this is one of the next stage.
I
So the project added the metadata.
Or patient history.
Yeah.
There was another question here, right?
I understand you used two-dimensional images. Is that right? Or you started from the three-dimensional OCD images?
The OCT 3D.
Okay, but what you passed to the networks, what was that? Was it sections of the 3D scan?
Do you mean if I pass all the data to the?
Because those look like sections. And I was wondering if they were taken on the same meridians.
No, it's all the image. Yeah, I just put the image later.
Okay, thank you.
Alim, you get the microphone there.
I have some comments. First one, and so in terms of your data selection, you select a group of healthy and a group of MI patient. So when you define healthy, so does it mean that the patient has no MI only, or this patient can have any eye disease? For example, they have either diabetes or other conditions that might affect your imaging. And my second comment is that for most of us, we have two eyes. So if you use the left eye to make prediction, if you use the right eye, can you get similar results?
Yeah.
Or on the other hand, if you use two imagery from two eyes as input, you can get better results.
Yeah. Well, the first question that you asked, we made we made some pre-processing when we select the healthy patients. When I say this, they don't have any cardiovascular diseases, and also they don't have nothing related to diabetes or high hypertension. That thing. That's why I said healthy patients. And the second is, well, yes, I'm using only the left eye. So, but the next stage is using both of the eyes. Thank you.
Thank you. Very quick question.
Yeah, it's a really quick question. Like for the pre-training, like you use all like healthy OCT images. Is there any specific reason for that? Like,
sorry?
Is there any specific reason for that? Like for using only healthy image or?
Yeah, we designed this way because the first stage is only for learning the features in the OCT. So and also because we have more healthy patients in the UK Biobank compared to the others for other cardiovascular diseases. So yes.
I was wondering like if there will be a like improvement using both the healthy and pathological.
We don't have so much data.
We need to wait until the UK Biobank people develop more disease.
Yeah, thank you for answering.
Thanks to you.
Thank you very much for your presentation. Thank you to all of the speakers who presented in this session. And I think, sorry?